Hello class, today we are looking at chapter 21 in our notes. So I have the chapter 21 outline ready for this. Go ahead and pause this and print it out if you need to, because that's what we're going to be going over. And in chapter 21, what we're going to be doing is looking at two groups and taking the difference or subtracting the events. So it's like two different groups and we're seeing if their percentage of them are different. So no difference implies that when you subtract them, it should be equal to 0, right? Because they're the same. And we're going to try to prove that they're not the same, that, one is bigger than the other, one is smaller than the other, or something like that. You have to meet the conditions first to be able to do one of these, and the conditions haven't changed from previous chapters. First thing is they have to be independent, except now we're talking about two different groups. So not only must each sample be independent, but the two groups must be independent of each other as well. And that's where we get these right here. They must be independent of each other. They need to be random. The data in each group should be drawn at random. And they need to meet the 10% condition, which means you cannot exceed 10% of the population. And on this one, success fail, both groups need to be large enough where you have 10 successes and 10 failures. Which, you remember, n times p is greater than 10, n times q is greater than 10 for 10 successes and 10 failures. So we have these formulas here, but I really got to show you a problem for these to make sense. So let's look at problem number 1. It says there's been a debate among doctors over whether surgery can prolong the life among men suffering from prostate cancer, and a type of cancer that typically develops and spreads very slowly. So in summer 2003, they published the results of some research. The men diagnosed with prostate cancer were randomly assigned to either undergo surgery or not undergo surgery. So among the 347 men who had surgery, 16 eventually died of prostate cancer, compared to 31 of 348 that did not have the surgery. So immediately when I look at it, I'm thinking, okay, the people that had surgery died at a less level, right? 16 out of 347 instead of 31 out of 348. It seems like we're going to be able to prove that the surgery was effective, but let's make sure. First thing they ask is, was this an experiment or observational study? That's from quite a few chapters ago. That was last semester, but hopefully you remember this. Whenever you assign a treatment like surgery, you make people go through surgery, that is definitely an experiment. You're not just observing, you're actually actively having these people do a surgery. So that is definitely an experiment on this one. Check your conditions. The samples are independent of each other. They were selected randomly, we're assuming that, and then it says they were randomly assigned. Less than 10% of the population, almost definitely, right? And 31 is bigger than 10, and 16 is bigger than 10. See, 16 and 31, those are both bigger than 10, so NP and NQ would be bigger than 10, so all those work. So we meet all the conditions. So this is how you set up a problem like this. You set up your two groups and give them a letter. Like S is going to be the people that got surgery, and N is going to be the people that got no surgery. So I set up S as surgery, as N as no surgery, like that. And for each one, you're going to need P, the percentage of them that lived, Q, the percentage that died is P, percentage that lived is Q, and N, the total number of people that had surgery or didn't have surgery. So you'll have that for each of them. So P, if you remember, the percent who died for surgery was 16 out of 347, which is, when I calculated, I got 0.0461. Q is just going to be 1 minus that, right? It's 331 out of 347, because 347 minus 16 is 331, and that's 0.9539. So with the surgery group, 4% of them died, and 95.4% of them lived. And there was 347 people, so N, S. So I use the S for this one, and then On this side for the no surgery, I use the N on that one. So on that side I use N. And 31 out of 348 died that did not get the surgeries. That is 8.91%. And 317 survived that did not get the surgery. So that's 91.09% out of 348 total. So they want us to create a confidence interval first. So the confidence interval is going to be 95% because that's what they tell us. So the z-value for 95% is 1.96. So let's take this data and use the formulas. I'll explain the formulas to calculate the confidence interval. The big formula here is the standard error, this formula right here. The standard error, when you have two groups like this, remember how to find standard deviation with two groups? It's Pythagorean. We got to add the groups together, right? So you actually have to add the groups together here. Actually, you don't Pythagorean here. We're just adding the groups together because it's two different groups. So we got P1, Q1 over N1 plus P2, Q2 over N2. See, it's like two different standard deviations being added together, right? And so I plugged in P1 and Q1, 0.0461, 0.9539 over 347, and P2, Q2, 0.0891 and 0.9109 over 348. And you'll see that matches the formula we have up here for the standard deviation and standard error. So you put that in the calculator, and what I got when I put that in was 0.01897. And when you put that in the calculator, it should, I used a Desmos calculator right here, and this is what it should look like, right here. Let me zoom in on that. That's what it should look like in the calculator. What you do is you square root it, and then I start a fraction, and you just type in your numbers, 0.0461. So get some practice on this, like head over to Desmos Scientific Calculator and get some practice. And you type them in and make sure you know how to get this in correctly. And you should be able to get your answer right here. The 0.0197 is what I got. 0.01897 is my standard error. So I calculated my standard error using that formula. And then I calculated my confidence interval. And here's my confidence interval formula on the sheet. It is P1 minus P2, because we're looking at the difference between the two, right? And if we can prove that the difference is not 0, then we can prove that the surgery was working, right? So P1 minus P2 is what we're going to do here for the confidence interval. So a 95% confidence interval. P1 minus P2, P1 was 0.0461, P2 was 0.0891. This was surgery and no surgery, right? And they're 4% apart, right? Like 0.043 apart, which is a lot. And then you do plus or minus the standard error, which is 1.96 times 0.01897. And I get negative 0.043 plus or minus 0.0372. And when I split that up into a lower bound and an upper bound, I subtract and add the two. This is what I get, 0.0802 and negative 0.0802 and negative 0.0058, which means the true difference between the two is somewhere in there. And you notice how 0 is not in this interval, right? 0 is not in here. It's all to the left of 0, which means we're 95% confident the true value is below 0. So we're 95% confident that this worked, that the surgery worked and it was effective. Since the entire interval, so I got my interval here, negative 0.0802 to negative 0.0058. And since the entire interval is under 0, there's evidence that the surgery may be effective here. So we've got compelling evidence that this surgery worked. Now, the calculations, you can do those, and they will work every time. And I wanted to show you kind of conceptually how we get the calculations, but you can do this in Stapplet too. And let me show you how. So I want you to go to Stapplet and pause the video if you need to and get Stapplet ready. And in Stapplet, I want you to go to 2 samples. So now we're doing 2 sample Z interval, a confidence interval. And I'm going to call this variable surgery effectiveness. And then I'm going to give my group names here. The group names are surgery, people that got the surgery, and people that did not get the surgery. So these are the 2 different groups. We split them up into 2 groups, people that got the surgery, people that did not get the surgery. And now we got our 2 different outcomes. They died or they survived, right? Now the people that got the surgery, only 16 of them died, right? Out of 347. So how many survived? 347 minus 16. So go ahead and get that. That is 331 that survived on the surgery. Now, no surgery, we had, how many of them died? 31. And how many survived? So there was 348 total, so 348 minus 31 is 317. And begin analysis. And we get our P and Q. You'll see those. Those are what we calculated. You didn't have to calculate all that by hand. You could do it like this right here. And we're going to do an interval of P1 minus P2. And a confidence level of 95%. It's interesting to call died the success here, but that's just technically what it is. That's what we were checking on. That's the key term we were looking for, the percentage that died. We want it to be lower, right? So we want the lower success rate there. So perform inference, and we get our same answer. See, we did all that calculation. We could have just done it on Stapplet right here and got the same answer of lower bound and upper bound. The only reason you would need to do it by hand like that is if they were to ask for the SE, you know, the standard error, and you would have to figure that out by hand because it doesn't tell you that right here. All right, that is problem number 1 and the notes. And that will be all for this video. I'll do problem number 2 on a separate video.